Hi, in this video we are going to talk about this problem. We are given a binary tree which may not be binary search tree. We need to return true if the given binary tree is binary search tree, and we need to return false if the given binary tree is not binary search tree. Let's see some examples. Let's see this example first. This is not a binary search tree because on left of 10 you have a value 12 which is greater than 10. So it's not a BST. On left everything has to be smaller. Empty tree and tree with a single node, they both are considered as binary search tree. Let's see this example. This is a binary search tree because for every node on the left side you have smaller values and on right side you have greater values. This is an interesting example. It's not a binary search tree because you can notice that 18 is there in the right subtree of 20 and 18 is smaller. So it's not a binary search tree. Right? This makes the question interesting. Now please pause this video and try to think of a solution that works in big O of n time, where n is the number of nodes in the binary search tree and tells you whether the given tree is binary search tree or not. A simple solution that many of us think when we take a look at this question first time is, for every node, simply check if its left child is smaller and right child is greater or not. If you find a node for which this property is not true, then you return false, and if this property is true for every node, then you return true. This approach does not work. For example, if you see this tree which is not a BST because 18 is there in the right subtree of 20, if I simply go to every node and check if its left is smaller and right is greater, it will be true for every node in this tree. For 20, left is smaller, right is greater. For 8, there is nothing on left or right, so we don't need to check. For 30, left is smaller, right is greater. For 18, nothing on left and right, so fine. For 35, nothing on left and right, so fine. So we return true in this tree, but it's not a BST because you have a value 18 in the right of 20, which is smaller than 20. This approach does not work because it simply checks for the consecutive nodes. It does not check the nodes which may be at a distance of 2 or more. Let us now talk about method 2, which is correct but inefficient. The idea of method 2 is simple. For every node, we find out the maximum value in left subtree and minimum value in the right subtree. And this node value has to be greater than the maximum in left subtree and smaller than the minimum in right subtree. So basically what we are checking, whole left subtree should be smaller and whole right subtree should be greater. So if you see 20, the maximum in left subtree is 8, there is only one node, and minimum in right subtree is 18. And we say this 20 has to be greater than 8 and smaller than 18, but it is not. So we return false. And that's how we figure out that this is not a BST. Had this been a value greater than 18, like had this been something like 22, then the minimum in the right subtree would have been 22, and then this property would have become true for 20. And please note that we not only check for root, we need to check for every node, right? For this node, the maximum in left subtree is 18 and minimum in right subtree is 35. And it's between 18 and 35. So this is fine for this node, but not fine for this. If any node does not follow the property, you simply return false. What is the time complexity of this? It's clearly big O of n square. Consider a skewed tree where you have a structure like this. There are n nodes. So for this node, you are going to find out the maximum in these n minus 1 nodes. For this node, you are going to find out the maximum in these n minus 2 nodes. So the time complexity is going to be n minus 1 plus n minus 2 and so on, which is n square. Let us talk about first efficient solution for this problem. And this is really an interesting, tricky and simple solution. What we do here is, for every node, we specify a range in which this node's value should be. For root, range is clearly minus infinite to plus infinite. Root can have any value. When we go down the tree from root, we change the range according to the condition whether we are going down to the left child or to the right child. If we go to the left child, we change the upper value of range. And if we go to the right child, we change the lower value of range. Let's see. In this example, this root can have any value from minus infinite to plus infinite. And for every node, we check whether its value is within the specified range or not. So for root, it's true because it's minus infinite to plus infinite. Any value is in this range, so it's fine. Now when we go down the left subtree, we change the range from minus infinite to 20. So this value should be from minus infinite to 20, and 20 is not included. In BST, we consider only distinct values. If there are same values, we say it's not BST. So this node has value in this range. It has value 8, which is from minus infinite to 20. Now when we go to the right child of this 20, we change the lower bound. We specify the range as 20 to plus infinite. And this node has value in this range from 20 to plus infinite. 30 is in this range. So we are fine with this node. Now when we go to the left of 30, we change the upper bound. This should be from 20 to 30. Now when we come here, we see that this node is not in the range. It should be in 20 to 30, but it is 18. So we return false at this point and we say it's not BST. Let us do one more example to understand it. For root, our range is from minus infinite to plus infinite. When we go to the left side, the range is from minus infinite to 80. When we go to the left of it, our range is from minus infinite to 70. When we go to the right of it, our range is from 70 to 80. And we can notice that every node is falling within the range, so we don't have any issue so far. When we come here, our range is from 80 to plus infinite. When we come here, our range is from 80 to 90. When we go to the left side, we change the upper bound, right? When we go to the right side, we change the lower bound. So when we are going to the right side, we say it should be from 90 to plus infinite. And every value is within the range which is passed. So it's a BST. Our code returns true for this. Let us now talk about C++ and Java implementations. So the idea is simple. We pass two parameters, min and max, to the function. When you are calling for root, you will pass min as int underscore min and max as int underscore max in C++. In Java, you will pass min as integer.min value and max as integer.max value. For every node, we check if this node's value is greater than min, if it's smaller than max. At the same time, left subtree of it also follows the same property and right subtree also follows the same property. So root has to follow this property, root has to be within the range, and similarly, recursively, it has to be true for the left subtree, recursively, it has to be true for the right subtree. That's what we check in this code. One thing you can notice is when we are calling for the left subtree, we are changing the max value. And when we are calling for the right subtree, we are changing the min value. Now, what is the time complexity of the solution? It simply traverses the tree, right? And with traversal, it's just passing two extra parameters. With these parameters, simply doing a traversal of the tree. So it's simply big O of n. And you can consider this as kind of pre-order traversal. It checks for the root first and then checks for the left subtree and right subtree. And this logical AND operator, it has this short circuiting, right? So if first condition itself becomes false, then it's not going to continue. So it's actually optimized also automatically. If your root itself or root of a subtree itself is not following the BST property, it's not going to recursively call for left and right. Now one more thing, in these functions, we are passing two extra parameters, min and max. So if somebody is asking you to write a BST function that takes only one parameter root, then what you can do is you can write this as an internal function and you can consider that function as main wrapper function. So you can call this function inside the given function with the initial values as minus infinite, plus infinite, and that's how you can solve that function problem. Let us now talk about fourth solution for is BST problem. This solution is also big O of n, and this is based on this fact: a binary tree can be binary search tree if and only if its in-order traversal is sorted. So if in-order traversal is sorted, then given binary tree is binary search tree, otherwise it's not. Let's see these examples. In-order traversal of this binary tree is 8, 20, 18, 30, 35. And you can notice that this is not sorted, right? 18 is after 20. And if you see this binary tree, in-order traversal of this binary tree is sorted. You have 60, 70, 75, 80, 85 and 90. So you have a sorted output. Now how do you implement this solution? One simple implementation is you simply do an in-order traversal, store the in-order traversal in an array, and then simply traverse the array and check if the array is sorted or not. Now the tricky part is, how do you solve this problem without using an auxiliary array? Basically using big O of h extra space for recursion only. Let us now talk about implementation. The idea of implementation is simple. We maintain a previous variable which has to be shared among all the functions. We do an in-order traversal of the given tree. In-order traversal means we recursively first call for the left subtree. Once you have called for the left subtree, you ensure that your previous variable has the value of last visited node's key, right? Once this is ensured, you check if current node's key is greater than previous or not. If it is not, then you return false. Once you checked it, then you need to check for the right subtree. So if you see, if we first check for the left subtree, then we check the current, then we check for the right, which is in-order traversal. And what are we doing in in-order traversal? We are mainly checking whether it is sorted or not. And how are we checking? We are checking if current is greater than previous or not. That's the simple thing. So in these implementations, in both C++ and Java implementations, we have a previous variable which is shared by all function calls. We have a base case which checks for root equal to null. If root is null, empty tree is always considered as BST, we return true. Then we check for the left subtree. And if left subtree is not BST, then we return false. Then we check for the current node. Once you have checked for the left subtree, your previous should be appropriately set to the in-order predecessor, the node which just comes before in order traversal. So once you check for the left subtree, you check if previous is smaller or not. If not, then you return false. Then you check for right subtree. So if you check for these two things, then all answer your depends upon right subtree. If right subtree returns true, then you return true, otherwise you return false. Let's do a dry run of this code for this example. We begin with the root. We have initially previous as minus infinite. In in-order traversal, we call for the left subtree first, and it's going to call its left subtree, which is null. And this null call is going to return true. So this left call has returned true for this node. Now we will check whether this is greater than previous or not. So this is greater than previous, so we are fine. Now we go to the right subtree. Right subtree is also null, which is going to return true. So we are fine for this node. Now the control goes back to the caller in an order traversal, and this left subtree has returned true. And before returning the true, this left subtree has also set previous as 8. Right? The previous is set here 8. Now the control comes here. It has already checked for the left subtree. It will check whether 20 is greater than 8 or not. 20 is greater than 8, so it is fine. Now it is going to check for the right subtree. Before it calls for the right subtree, it's going to update the previous as 20. Right? Before we call for the right subtree, we update the previous. Now it calls for the right subtree, and right subtree also does an order traversal. So it goes to the left of it. And when it goes to the left of it, it also goes to the left of it, ends up with a null. It returns true. So the control comes back here. And when control comes back here, it checks whether this is greater than previous or not. So this is not greater than previous. You know, previous is 20 and this is 18. And this is where we return false. And we say it's not a BST. What is the time complexity of this solution? This solution does a simple in-order traversal. So time complexity is big O of n. How much auxiliary space it requires? It requires auxiliary space big O of h, which is same as in-order traversal auxiliary space, where h is height of your given tree.